Hello, everybody. Thanks for coming. This is the last lecture in Module 3. And as promised, we're going to come back and do 2.9, which is the one we skipped in the previous lecture. Okay? And in addition to looking at 2.9, which is about chemical reactions, as kind of like a function of breaking and forming covalent bonds, I'm also going to be throwing in 5.11. Right? And you can skip forward your textbook. And if you compare the titles of these two sections, you'll realize why I'm doing this. It's kind of hard to talk about chemical reactions once in chapter 2, and then talk about chemical reactions again later in chapter 5. Chapter 5 will be concerned largely with the energetics, but it makes a whole lot of sense for us to talk about the energetics right now. So please be flexible with me here and do a little bit of skipping around. We'll have to do this from time to time over the course of the semester, okay? And so, yeah, we're doing more chemistry today. Chemical reactions, a big part of our BIO110. They're fundamental in biology. Pretty much everything that we look at throughout the semester is going to be involving chemical reactions of one form or another. And so it's a good idea for you to become familiar with chemicals and what we mean by a chemical reaction. You're already familiar with things like this kind of symbol, this kind of chemical notation. So if I write CO2, you should know at this point that CO2 is one carbon. It's covalent bonds to two oxygen atoms. And if you try to work it out, you'll realize that the carbon has to be bonded to four things. And there are four bonds coming to carbon. There are two bonds attaching to each oxygen. So it kind of makes sense that you could make those four bonds on the carbon by putting two bonds on one oxygen and two bonds on the other oxygen. Okay. Whereas if you look at a molecule like H2O, the only way that H2O is going to be working and still maintaining those basic rules of covalent bonding. Remember that each kind of atom has a certain number of vacancies in the valence shell that it needs to fill. Hydrogen has one vacancy, oxygen has two vacancies, and that's why oxygen is always going to be forming two covalent bonds, whereas hydrogen is going to be forming one, nitrogen forms three, and carbon forms four. Right? So you know from a previous lecture that we draw water molecule like this, where we've got H and another H. And if you look at this, you'll realize that the H's all have one covalent bond. The oxygen has two covalent bonds, and you'll realize that these are good, legitimate molecular structures, right? And so you're getting kind of familiar with that, be able to recognize basic molecules. You're going to be getting much better at chemical recognition as we move forward from here, right? But the thing that we're thinking about here is, well, these covalent bonds that form, right? This covalent bond here, these covalent bonds between carbon and oxygen, they represent something that's occurring between the atoms of carbon and oxygen, or between the atoms of oxygen and hydrogen, that's making them more stable, inherently more stable, right? And so you're used to the idea that, well, H2O is far more stable compared to an O and an H and an H, right? The situation with the oxygen and two hydrogens separate is that these are incredibly unstable because they don't have complete valence shells. Afterwards, after a covalent bond forms, after we take this oxygen atom and these two hydrogen atoms, and we allow them to gain their happy state, they're far more stable as a result, right? And so the idea that we have stability increasing stability with the forming of covalent bonds is also bringing us to a lower state of energy, right? You had to compare things on the right, things on the left. Okay, if we start off with one oxygen atom and two hydrogen atoms, and form a water molecule. The one on the left, the water molecule, is far more stable. It's going to be at a lower state of energy, whereas the oxygen atom and two hydrogen atoms would represent a higher state of energy. Okay. Now, this is bringing us to another kind of central idea, and it has to deal with one of the basic laws of nature. Right? So among the many laws of nature that we sometimes refer to in a biology class are the basic laws of thermodynamics. Right? And the very first law, this is the only one that I'm going to be pointing out here, is it's sometimes called the conservation law. It's the conservation of matter and energy. It basically says that we can't create matter or destroy matter. You can't create energy from nothing or destroy energy. If you have energy at the beginning of the reaction, there has to be the same amount of energy at the end of the reaction. If you have matter at the beginning of the reaction, the same amount of matter has to be there at the very end, right? And so when we take this into consideration, if you have H, an H, and an O to begin with, and you allow them to form a covalent bond in the form of H2O, right? If this is a chemical reaction that's occurring right here, it's pretty easy to account for the matter conservation because we still have the oxygen, right? We can still account for the two hydrogens. And so that allows us to satisfy the first law in terms of matter. But when it comes to energy, realize that we have high energy on this side, low energy on the right-hand side. And consequently, the energy that we have afterwards has to be equal to what we had before. And therefore, there must be an additional energy. Right? And so if you take the amount of energy that we have in the water molecule, add some additional energy, then you could account for all the energy that's there at the very beginning. Right? And so the amount of energy has got to be equal on both sides of the chemical reaction. And because we're ending up with a more stable product, water, as opposed to the reactants, oxygen atoms and hydrogen atoms, there must be a substantial amount of energy being released, right? And if we end up with energy coming out of the reaction, energy out, we refer to this type of reaction as exergonic. Exer meaning outside, gonic refers to the energy exchange. The exergonic reaction is an energy out reaction. Okay? And that's the case here because we're ending up with a much more stable product. So if we go from less stable to a more stable, we're going from higher energy to lower energy. And with the first law of thermodynamics, we know that we must account for energy before and after, and that results in some energy released. And those are reactions we identify as exergonic. Okay? That's term number one. And the opposite, the reverse, is to say that if you break covalent bonds, break covalent bonds. In other words, if you start off with a water molecule and it's got these two covalent bonds that bring all of the matter there, all of the three atoms into their happy state of having complete valence shells. And we simply break apart those hydrogens and oxygens to end up with oxygen and a hydrogen that aren't covalently bonded, that don't have complete valence shells, right? The result is going to be a much higher energy state. than what we have at the very beginning, right? And so this is a reaction that would not be, I mean, if we don't have any energy coming into the reaction, this would be something that would be violating a basic law of the universe. Okay? And we don't ever violate the basic laws of the universe. That's one of the things that a scientist is not allowed to do, right? We're scientists for a reason here, in order to account for that conservation of energy, because we're already able to account for the conservation of matter. Two H's on the right, two H's on the left, one oxygen on the left, one oxygen on the right. The matter is still there pretty much in the same way that it was at the very beginning. Okay? The energy, however, is much higher. In order for this reaction to actually satisfy the first law, we have to have an input of energy. Okay? There has to be some energy coming in from outside of just the water molecule. There has to be an energy input. And with energy coming in, call that kind of reaction endergonic. Energy in. Right? And so inherently, breaking covalent bonds is always going to be an endergonic reaction, because we're always going to have to tear apart something that makes molecules inherently stable, whereas forming covalent bonds like we're doing on this diagram, we're always going to be increasing the stability, and therefore forming covalent bonds is always going to be an exergonic reaction. That's completely fundamental, right? And so having said that, we have to come back to our basic premise that when we do chemical reactions, okay, when we have a chemical reaction with reactants maybe on one side of the reaction and an arrow pointing towards products, and the products being on the other side of the chemical reaction, when you look at them really carefully, we don't really have a different number of covalent bonds before and after. That never really happens. The number of covalent bonds is always going to be the same. Okay? What's different are the bonds that are there. Basically, in order to make a chemical reaction move forward, some people would say we're rearranging the bonds, right? Breaking some and forming other covalent bonds. Okay? And so you take what we've been talking about so far, you realize that covalent bonds, when they form, is going to be an energy releasing reaction phenomenon, whereas we have to break chemical bonds in order to make to reestablish them with other atoms. The breaking apart of covalent bonds is going to require energy, and what we're going to be having to do at the bottom, and we're kind of skipping to the end right here, is to say, well, whether that overall reaction is going to be endergonic or exergonic, whether it's going to have an energy source bringing energy from the outside to drive the reaction forward, or whether it's going to be a reaction that is not going to need an outside source. In fact, it'll happen kind of spontaneously because we've got the laws of thermodynamics behind us, right? Those are going to be exergonic reactions. Whether we're an endergonic reaction overall or an exergonic reaction overall is going to depend on the energy balance of the covalent bonds that are forming and breaking. Okay, so that's kind of like my preamble. And now we're going to be moving over to the textbook share. Yeah, this one is really kind of nice because it kind of talks about the things we've been discussing so far. It identifies what we mean by reactants in a product. This is not even a biological example. Oh, wait, what happened to my annotation bar? In a second, give me a minute and okay, now I'm gonna, all right, everything's under control now. Sorry for the delay. This would be a good example of a chemical reaction, right? Two hydrogen molecules, right? Notice that these are H2. Okay, now, we're not talking about hydrogen atoms. We're talking about hydrogen molecules. Okay, and this will be an oxygen molecule, O2. Okay. And so we're not, fundamentally, you might look at this and say, hey, that's kind of like similar to what Ihara just said in the video. But no, this is actually something that, in which we're starting off with 3 covalent bonds on the left-hand side of the reaction. Here's the arrow, and we're ending up with no, actually we've got 4 covalent bonds here because the oxygen is a double bond. I'll show you that in a second. And we're ending up with 4 covalent bonds over on the right-hand side of the reaction. And let me go ahead and scroll. Clear the drawings here. I'll get my mouse back and I'll scroll up. And you could actually see this chemical reaction in living color, right? And so looking over here, here are the 2 molecules of hydrogen in white. We've got a bond here, a bond here. Those are covalent bonds between hydrogen atoms. With the oxygen, we've got a double covalent bond, 2 more bonds between that the oxygens in that atom, in that molecule, between the 2 atoms in that molecule, right? And at the very end, we have 2 molecules of oxygen. We also have 4 covalent bonds involved. Bond between an oxygen and a hydrogen, and a bond between an oxygen and a hydrogen. We have 4 of these. Okay, so here we're ending up with 4 OH bonds. Here we have 2 bonds between H and H, and 2 bonds between O and O. Okay? And so I guess what we're saying here, looking at this, you'll realize that in order for this reaction to take place, where hydrogen is going to join with oxygen and form water, okay, we have to break this bond. You have to break this bond, break both of these bonds, right? That's part of the chemical reaction. That's going to require energy in. Okay. To break those bonds. Okay. And at the end, we're going to get energy out, right? Energy out when we form these bonds. When these bonds form, right? Oxygen, hydrogen, oxygen, hydrogen, oxygen, hydrogen. All of these bonds, as they form a water molecule, as they form to create a water molecule, are going to be exergonic, and energy is going to be released, right? So going back to what we were talking about before, right? How do you determine whether this overall chemical reaction is going to be exergonic or endergonic? Well, it's a balance, right? The energy out. Is it more energy or less energy than the energy that's required in order to make those initial covalent bonds break in order to make the reaction go forward, right? Because if the energy in is greater than the energy out, then it would have to require energy coming in, and therefore it would be an endergonic reaction, right? On the other hand, if the bonds are breaking relatively easily and we're getting bonds forming that are going to be far more stable, then the energy out would be greater and we would have an exergonic reaction. All right? Yeah, and so yeah, I'm being really sneaky here. I'm sneaking in some energy related discussions as we're talking about the basic process of chemical reactions. Now here's here's my rationale for putting all of this stuff together, right? If you look at the title for this is basically chemical reactions, make and break chemical bonds. And they put for some reason, they put this chapter, this little section of the chapter right between hydrogen bonds and the properties of water, right? Which is kind of weird, right? To me, the chemical reactions are very central, and we need to talk about them as we're going into exactly what we're covering next, which is reactions that are going to be creating proteins and carbohydrates and lipids and nucleic acids. We're going to be talking about chemical reactions. We're also going to be needing to think about the energetics of those reactions as well. And so what I did was I did a little search, and I found that if we look at for section 5.11, chemical reactions. Okay. Here's that other part of the textbook that we're actually bringing in as we're talking about chemical reactions here, right? And this is exactly what we were talking about before. If you start off with reactants that have a higher energy compared to what you end up, what you end up with, like this might be H. Oh, oops, this might be H and O, right? Those are our reactants. And the first thing that I drew, and I said here we end up with H2O products. There's going to be energy released, right? In the one that we just went through in 2.9, you could say, well, we're starting off with 2 molecules of H2 and 1 molecule of oxygen. We're breaking apart the covalent bonds there, and that's going to require energy coming in. But overall, the energy coming out is going to be greater if we're forming 2 molecules of H2O, right? And so the energy released has got to be exactly the difference between the energy status of the reactants and the energy status of the products. Okay. The reverse of this. Okay, so we're talking about reactions that are exergonic reactions. Energonic reaction is going to be the opposite. Okay, so if, for example, I'll do a different example for you, right? Maybe one that's a little bit more relevant to the biology that we're coming towards, right? If we're looking at the reactants being 6 molecules of carbon dioxide and 6 molecules of water, right? You can count up all of the covalent bonds that are there and say the product is going to be 1 molecule of C6H12O6 and 6 molecules of O2, right? In other words, so if you look at the number of covalent bonds, that's an O, not a 6. So 6 molecules of oxygen. If we actually have 6 molecules of carbon dioxide and 6 molecules of water, and end up with 1 molecule of glucose, that's this C6H12O6 molecule, and 6 molecules of oxygen. The number of covalent bonds are exactly the same. We're actually going to do this later on. Okay, and plants do this all the time. This is called, we call it photosynthesis, right? What a cabbage does is it takes CO2 from the atmosphere, it takes water from the soil, and it undergoes photosynthesis. It has light receptors in its leaves called chlorophyll, and the chlorophyll converts the energy. And at the end of the story, we actually end up with a molecule of glucose. And we're also producing 6 molecules of oxygen in the process. Okay, now plants are able to do this because they've got an energy source. The energy source for plants is, of course, the sun, right? So solar energy is going to be the energy source that's going to be driving this endergonic reaction. I need to change colors here, because otherwise you can't see. Solar energy, and this would be the endergonic reaction that is photosynthesis. And I'm hoping that I haven't lost you here. You can actually see, okay, well, yeah, carbon dioxide, water are the reactants, glucose and oxygen are the products. Right? That's exactly what a plant does, when it makes more plant, when a plant grows. And that requires energy in, and plants are energy, they're solar receptors, solar converters. That's exactly what a plant does. It converts solar energy into a product into energy that's in the form of chemistry. In this case, glucose represents a higher state of energy compared to the reactants that we're starting off with. This would be low energy. Okay. It's actually more stable compared to the product, higher energy. Right? And so, yeah, it actually describes what I just said down here. Photosynthesis is the process by which plant cells make sugar, and that's a good example of an endergonic process. Okay. Now, I think I'm going to go back to my original share here, which is the whiteboard. And looking at everything that I've given you, I've pretty much covered everything except for these terms. All right, so I'll be doing a little bit of a review, and I'll add the term exothermic and endothermic because those are actually pretty easy for you to relate to. I wanted to use the generic term exergonic and endergonic first because those are the terms that are really more appropriate for what we're doing in class. Right. Okay, so let's go through this. Chemical reactions are fundamental in biology. That's why we're doing this. Chemical reactions involve reactants. Those are the things that go into a chemical reaction, and products. Those are the things that come out of chemical reactions. Okay. And well, we analyze, we can dissect a chemical reaction into what exactly is happening. It's always going to involve rearranging covalent bonds, breaking some bonds and forming other covalent bonds. Okay? Not every bond is going to be broken and reformed, but there's going to be at least a few covalent bonds that are there at the beginning that aren't there at the end, and a couple of covalent bonds that are there at the end that aren't there at the beginning. And that's what makes the products different from the reactants. That's what we mean by chemical reaction, right? Because if what you start off with is exactly the same with what you end up with, that would be a non-reaction. That would be this thing stays the same. Right? With a chemical reaction, things are turning into something else. And in this particular case, we're always going to involve, we don't have any conversions of lead into gold. That's not the kind of reaction that we're talking about here. We're talking about a reaction in which we're just rearranging the covalent bonds, breaking some bonds, and forming others. Okay. Now, the connection with what we've been talking about so far in the last couple of lectures is that we're really forming covalent bonds and we're breaking covalent bonds, right? And you know from the past couple of lectures that covalent bonds are really important for molecules because they make the molecules happy. They make the atoms happy. It gives the atoms the sense that they've got a complete valence shell of electrons. Right? And that's what brings them into their stable state. That's what brings them to states of lower energy. Right? And so if you form a covalent bond, you're always going to lower the energy of the matter. If you break covalent bonds, that's going to require energy to go in because we're taking something that's inherently pretty stable and destabilizing it. We have to move away from that situation of having complete valence shells, right? And so, yes, this is also very true. Forming covalent bonds, always exergonic. Okay? Breaking covalent bonds, always endergonic. And when you take a reaction like CH4 plus 2O2, giving rise to CO2 plus 2H2O, right? This would be, this is a reaction that if you have a gas range, this happens when you cook your food. This is methane gas. Oxygen is being recruited from the air in your kitchen, and the waste products that are coming out as a result of the combustion of natural gas are CO2 and water. Right? So we know that this is exergonic because we're getting heat from it. All that heat that's produced when you combust, when you burn natural gas, is very clearly evident to us, right? It's also exothermic. because the form in which the energy being released is coming out in the form of heat, right? So we use thermic as kind of like a surrogate for the energy, when the principal way in which the energy is being realized is heat energy. A lot of chemical reactions may be producing some heat, but it's not necessarily the thing that we're focusing on. We're not measuring the chemical reaction by the temperature change that's occurring. We're measuring the chemical reaction by the kinds of products that are forming. And so we tend to think about exergonic. We tend to use the term exergonic as opposed to exothermic, right? Endothermic reactions are exactly the opposite. So if you were to have like one of those ice packs, right? Those chemical ice packs, most of you are going to become nurses, so you know about this. You know that you've got these $30 packets of stuff that are there in medical kits with little glass ampoules on the inside. If you break the glass ampoules on the inside, shake it up, the chemical reactions occurring inside of this little pouch turn the whole thing really cold, right? And so I don't know what the chemical reaction is there. I could probably look it up. You could probably look it up. That's what Google's for. Okay, but I think what's obvious here is that there is a change in energy. The reactants are coming with a much lower state of energy, right? And the products have a much higher state of energy, and so energy must be drawn in from the outside. The energy that's being sucked up from the outside of the bag, in other words, the bag turns cold, is all the heat that's being taken in by the bag in order to drive this chemical reaction forward. That would be a really cool example of an endothermic, not endothermic. Endothermic would be one in which heat energy is absorbed, although we, in our class, we're usually concerned with the energy generically because we'll be using other things to think about energy, like chemical energy forms of cells, as opposed to always relying on heat as being the form of energy that's occurring during any type of energy transduction inside of cells. All right. And so, yeah, again, more crucial ideas. I tend to focus BIO110 on things that are necessary for you later in the course, later in your careers as most of you are pre-nurses or pre-health, pre-dental hygienist, pre-physical therapist. And so all of the concepts we'll be talking about here are kind of like hand-selected things that are going to be pretty important for you vocationally, right? And so I think I've covered everything I need to, and I guess you're ready to move into the next module, which will be taking on the kinds of molecules that life is made out of: carbohydrates, lipids, proteins, and nucleic acids. But there's going to be some preamble-y material before that, okay? All right,